So thank you for joining this tutorial, and I hope it would be worth of your time and would be interesting. And thank you, Boris, for the introduction. But first, I would like to take a couple of seconds to call for peace in these uneasy times. So let's start. Cloud computing is at the cortex of the modern digital economy. And it is the one that defines the pace of the scientific progress and the pace of our community is going. For example, half of the data produced is processed by businesses today is processed in cloud and is stored in cloud. In cloud computing, the providers are responsible to maintain large compute sites called data centers with huge fleets of servers. At the same time, service developers rent the necessary compute nodes, servers from the providers to deploy their services in cloud. There are two conflicting trends that manifest themselves throughout the years. First, the complexity of the cloud infrastructure is increasing as systems of larger scale being deployed, and the heterogeneity of the computer resources is growing as well, with not only CPUs, but GPUs and custom accelerators being deployed at scale. At the same time, the pressure on cloud service developers is growing as well, pushing them to move their products to market faster, roll out upgrades, and at the same time spend less on operational costs for the services. In response to these conflicting trends, the providers came up with a new paradigm of cloud computing called serverless, in which cloud infrastructure is abstracted away from the consideration of service developers. In other words, servers are still there, but their existence should not concern the developers when they are writing their services and applications. Given this serverless premise, businesses started to adopt serverless really quickly, rewriting their applications in the new serverless programming model. To give you just one example, in 2018, analysts registered that the adoption rate of serverless almost doubled in a single year. The number of serverless applications being deployed doubled in a single year. That you can also, from this chart, you can see that adoption pace of serverless is higher than many of the hyped concepts like machine learning and the Internet of Things. So it is fair to say that today serverless has penetrated all areas of computing, from e-commerce to banking. And now serverless has become the next dominant cloud architecture. So the goal of this tutorial is to introduce you to this new next generation computing and show you both the perspective of an application developer, of what the developer and clients care about, and also a systems researcher. As I think most of us in this audience, virtually or physically, from the systems community. So it's important to combine these two perspectives. We will show you how to develop and deploy applications in AWS Lambda, which is the leading cloud to date. And then in the next, in the afternoon section of our talks, we'll move to the vHive ecosystem, which is the framework for experimentation, and it includes a lot of tools and technologies and benchmarks that serverless researchers need. Throughout the day, you will have a lot of hands-on sessions, which will show you how to use vHive and how to work with AWS in particular for and conduct performance analysis and pursue pursue research goals in different subfields of computer systems. I also encourage everyone to ask questions as we go. So if there are questions in the audience, please let me know through Slack. And I'm talking to organizers in this case. So the tutorial agenda is in European time, so we'll stick to it. There going to be another one, another session for the setup. So I encourage people to come a bit earlier so that we save time on setting up. There are going to be a lot of hands-on sessions where in most sessions you will be supposed to running commands as we instruct you. So we'll get hands-on experience how to do things. So are there any questions regarding the logistics? Maybe someone at the laptop could actually say something, like if there are any questions to the audience or not. Boris, I cannot hear you. I think it's mute.
There are no questions.
Okay.
Unmute. Echo online. We'll keep it unmuted.
Is it an echo?
No, I think it's fine.
Hi, Dmitrii. One small question. Is a Windows laptop enough for all the hands-on, or do we need a Linux terminal?
So you will, on your laptop, you will just need a browser like Chrome, and you should be able to SSH to a Linux machine in Google Cloud.
Yes, okay, that should be enough, right? Okay, thank you.
Yeah. So I think I already sent the SSH keys. Yes, I already sent the SSH keys, so this is all you need for now. All right, so if there are no more questions, let's move on. So let's talk about serverless now. In this introductory talk, I'm going to introduce you to the programming model called also function as a service, and touch upon the key aspects of cloud infrastructure for serverless, in particularly the one used for scheduling and placement, and the advanced technologies used for isolation of different functions running in the fleet. And I will finish this by having a discussion about the current state of serverless as a community. So serverless allows service developers to focus on writing their code as a set of functions, whereas the cloud providers take care of all the heavy lifting, that is automatic scaling of function instances of each function according to the traffic changes. This labor division facilitates time to market for software products, improving developers' productivity. So let's say the developers need to write a video analytics application with two functions. In this case, the first function would take video fragments from a camera and decode frames from these fragments, calling the second function to recognize the objects in these frames. The developers can compose them using function calls, just like in conventional programming, albeit it's serverless function calls. However, so at the same time, developers enjoy the flexibility of serverless pay-as-you-go, pay-for-what-you-use model, where the developers pay only for functions being executed according to the CPU time they consume and the memory resources they need. And this is why serverless enables better developers' productivity and lower operational costs compared to conventional clouds. From the serverless cloud provider perspective, the situation is totally different. To accommodate changes in the invocation traffic in front of each function, the provider scales the number of instances according to the load on this function. And a function can have an arbitrary number of instances from 0 to virtually infinity. And this can change at any point in time based on load. Making these decisions intelligently is critical for the infrastructure to be efficient. Because if there are too few instances, the performance would be poor, because spawning new instances on demand takes time. It's also called cold start. While spawning too many instances is suboptimal because it wastes resources. For example, it occupies memory. So a lot of innovation is efforts is there. So there are many more challenges and responsibilities that providers have to assume and tackle to make serverless cloud efficient. To look at the serverless clouds from the evolutionary perspective, we can show it in the following diagram. Compared to on-premises, it has almost all the layers of the hardware and software in the provider zone of responsibility, while clients focus only exclusively on functions. Compared to conventional cloud, this cloud is still responsible for running operating systems, like guest operating systems, and scaling, while function as a service pushes this to probably the most complicated layers of the stack down to the provider. So this is the main change that serverless computing brings to cloud. I think if there are any questions on the programming model side, we can discuss them now. All right, so when we talk about the requirements from the client side, they are very similar to the requirements that conventional cloud has. So for example, the high availability requirement assumes the need for low response time and durability of the data that is already in the cloud. At the same time, the clients want the resources they ran from the cloud to scale automatically with their load. They don't want to be overcharged for provisioning more resources than they actually need for the most of the time. In conventional clouds, this is what happens usually. The developers have to over-provision their resources for the worst case. Serverless solves this problem by provisioning on demand. And that is why serverless in many cases is used for provisioning for the peak load, while conventional infrastructure may still be used for provisioning for the regular load. Security requirements are key. And this is something that that any company cannot make compromises on. And this is why provider has to care about security first of all, even before the performance. And the requirement now is extending from defending jobs from one another to defending jobs from the provider itself as well. Because there are many bugs that appear from time to time, and there are malicious providers and so on. And the less control the developer has over the infrastructure they execute on, the more vulnerable they may feel. So it is natural. From the provider side, their goals are make sure the utilization of hardware resources they have is high, because this translates directly into the costs. And that is why they aggressively collocate as many jobs as possible and power off the nodes that are not in use. So in this case, serverless is more about packing rather than load balancing across the fleet. I would say packing the jobs in the fleet is the first goal, while load balancing is sort of secondary, and it's more like an optimization problem. At the same time, while there's so much responsibility offloaded to the provider, the number of CPU cycles going into the provider side is also much bigger than in conventional cloud. So one of the priorities that provider have on their plate is to decrease the impact on the overall performance that their infrastructure has, and memory resource occupation as well, memory footprint imposed by system layers. And security is the foremost problem. So let's move to the cloud infrastructure now. And we are going to start with discussing the cluster scheduling, starting with conventional scheduling and moving to serverless. So as you may guess, serverless data centers are just the same ones that cloud has run before. So it's just the same data centers which have tens of thousands of compute nodes in huge deployment managed by the providers, where the providers are responsible for all aspects of managing the hardware and software, and its security, fault tolerance, and other features. At the same time, these data centers are scattered around the globe and grouped in the availability zones that you may hear, like US West 1 or Europe Central 2 or something like this. This is usually assumes about 3 data centers grouped in a single availability zone. So these are 3 data centers about 100 kilometers one from another for fault tolerance. At the same time, the new trend is the emergence of edge deployments, which means before you could have deployed applications in particular data centers, while today it's also possible, or soon it will be possible for some providers to deploy across data centers, which means the provider would migrate the jobs to the location where they need to be executed based on demand. So if you look from the perspective of packing the workloads on the data center fleet, I took the following diagram from one of the talks about Borg from John Wilkes from Google. So in this diagram on the right, you can see the CPU utilization and memory consumption across the fleet on the y-axis, and on the x-axis you can see different servers in the fleet. So this diagram shows how the providers achieve the goal, or like what the goals they actually achieve when they try to pack jobs on the data center fleet. So what they do, they try to maximize CPU consumption and memory consumption at the same time. leaving as few blank gaps as possible. At the same time, it's not always perfect. So there are stranded resources. For example, when a machine has all the CPUs busy but has some memory, and this is usually the room for innovation, for better scheduling, placing, and so on. At the same time, there is continuous monitoring of cluster nodes and the resource reclamation and migration of the jobs. So this is what conventional scheduling goals are, and they stay pretty much the same in serverless case as well. So let's talk about how the state of the art of conventional scheduler actually works. The scheduler we're going to talk about is called Kubernetes, which inherited from Google Borg. And today it's used pretty much by any cloud provider. The scheduler the scheduler's role is the same to the role of Linux as an operating system on a local node in the context of a cluster. So what it does, it allocates resources such as CPU time and memory resources to the jobs that need it. The client deploys jobs by sending them their requirements to cluster scheduler. The cluster scheduler runs on a node called master node, which of course can be replicated. And this is the central component of the control plane of this solution. It's a highly available cluster scheduler with a replicated database called etcd, which contains the metadata and of the current status of the entire cluster, which can be as big as a data center. And some people even try to scale it to many data centers at the same time. So basically, this is a knowledge base for all jobs, and all resources are being allocated throughout the whole data center. There are parts of control plane running on every worker node, which is just a server, physical or virtual, called kubelets, which receives commands from the centralized scheduler and implements them in the language of runtime supported by this worker, like virtual machines or containers. There are services that can be deployed, and these are the client, when it deploys a job, it deploys a service which doesn't have resources attached to it by default, but it's allocated by the scheduler in the granularity of pods, which act as the instance of a service. At the same time, these are units of scaling. It's easy to think about pods as a one container per pod, but at the same time, it could be several containers connected in a chain or in a flow that can be scaled together. And the worker nodes are the like physical or virtual nodes, doesn't matter, which host these pods, and their resources are allocated to the pods by the scheduler itself. In this example, you can see that traffic is going into a pod called front end, a pod, but also a container in our in this diagram, or could be several containers. And this pod would multiplex the load between two application pods, for example, for web serving, which actually run the business logic of the application. But everything in this architecture is a pod, and everything that runs in the pod can be a container, for example. So what's wrong with this model, and why it needed a change for serverless? The problem with that is, in this case, the provider only takes responsibility for the hardware and the hosts, but the client still manages all the infrastructure, and it has to scale the resources in terms of the number of pods allocated to each application that runs in the system. And having it as a manual job, it takes time and increases the reaction time when the load suddenly spikes, which inevitably leads to more resources allocated and over-provisioned for the worst case, which decreases the efficiency of the system in general. And this applies to any resources of this data center, from CPUs to memory and disk and all the rest. So the main goal of what serverless does is to break this dependency and on the manual job of a client. So let's look at one of the state-of-the-art solutions for serverless, which is open source, so we can study it in detail, which is based on using Kubernetes as the scheduler of cluster resources. Knative also is a part of CNCF Foundation, Cloud Native Computing Foundation, contributed by Google recently. So for Knative, it works in the following way. The client deploys functions, so it still deploys services, if you like, but it completely offloads the management of the resources to the automatic system. At the same time, it doesn't require any changes to Kubernetes, which still manages the resources on its own. The user only provides the codes and defines what triggers these functions that they wrote. So this is the same application that we briefly discussed in the previous slide, where there's a traffic coming to the front end pod, and then it gets multiplexed to the actual business logic, the replicated in pods. But you probably noticed that there was much more red, which means user controlled, in the previous slide, while in this slide you can see that most of this is blue, which means it's provider controlled. However, there is a distinction from the roles of Kubernetes and the roles of Knative. So Knative is also a collection of pods and containers running inside them. So now the actual code written by the user runs only in function handles, and that's it, while the rest is controlled by the provider itself. So in this case, there is different pods responsible for the control of the resources. When the traffic comes into the front end, it first gets into the activator pod, which acts as a load balancer between function instances. So it acts as a centralized queue, which waits for the request to be forwarded upon allocation in the queues, which is also a container, in front of each function instance. Of course, there could be optimizations where the traffic can be forwarded directly to the pods to the function instances when it's possible. However, under load, activator pod is always some buffering. At the same time, there is a infrastructure that monitors the load in front of every single instance and sends requests to Kubernetes to the Kubernetes scheduler to spawn more function instances if the traffic increases. But particularly, it looks at the buffering at the function instances in components called kuproxy. And when the number of requests waiting for execution on a particular instance exceeds the threshold, the autoscaler pod informs the scheduler to spawn more instances. So if there are any questions how serverless infrastructure works, with the example of Knative, it would be good to discuss it now. All right.
Maybe I can ask a question. From poetry. The scheduler is receiving metadata, right? I mean, is the CPU and time and so on. So each pod has to send back this metadata to the front end, and the front end back to the scheduler, or it's synchronous all the time to send back the CPU utilization time. Which pod is basically free or not, something like that?
Yeah, very good question. So what's important is allocation is done in pods, right? So only when the number of pods needs to be increased or decreased, the scheduler receives requests and updates its metadata when it actually makes decisions on spawning new pods. So the whole infrastructure in light blue works without notifying the scheduler unless it's necessary. So all these requests and responses affect the cluster metadata only when thresholds being exceeded, and periodically, of course. Thank you. All right, so.
I think there's a question in the chat.
Yeah. Now, was there a question?
There's one in the chat. The Zoom chat.
To be honest, there is an echo, so I cannot hear very well.
There is a
Maybe-
question in Zoom chat.
Can you read it, please?
Oh,
Sorry. Yes, just 1 second.
Oh, okay, I can see it now.
So, okay.
Maybe I can read it then. So function pod 1 can have only one function handle or can have multiple. So pods is the granule of scaling, right? So that is why it has to be a 1. But it's also important to know that the pod on its own doesn't consume resources, or to some extent, it does consume like a network namespace, for example. It does have its own, but that's about it. It doesn't have like particular memory resources allocated to it. It's not a container. That is why it's rather cheap to have many pods as compared to packing things into pods. All right, so let's talk more about the other aspects, such as minimization of the infrastructure overhead and maximizing security. So in the systems community, there are 2 ways of solving this problem. One with the lowest possible overhead is Linux processes. And another way is to use virtual machines, which is the most secure, but at the same time, the biggest overhead. So in the case of processes, the problem is that the applications share a lot, like a big part of their stack. And any of these applications, if it's able to gain root access, may compromise the host. In the virtual machines, a big fraction of the code is unique for each application. So there's a high degree of isolation, but this comes with a lot of overheads. So none of this solution is ideal. So there are two ways of solving this issue, like taken by systems researchers. One is to make the process isolation stronger. For example, this resulted into like virtualizing different components of the host stack, such as the network namespaces, process tree, and file system virtualization. And also system call filtering, because system calls are usually like the most widespread method of compromising the system. So for example, by using malicious arguments or some arguments that put the system in a particular position that the attacker wants it to be. And the other way is to make the virtual machines more lightweight and avoid overheads connected to like increased time and scheduling or memory allocation and so on. But the problem there is, one of the problems there was that virtual machines have to support a lot of different hardware emulation devices to make sure everything runs. And this was one of the main issues that actually slowed virtual machines down. So what's important to understand is the concept of containers. In containers, containers allow to isolate the bulk part of the stack without the overheads of a virtual machine. And this resembles the first approach, which was realized by Docker in their ultimate automation of all this namespace, file system, and other types of isolation. It's also important to know that containers and this type of isolation, it's still needed even for virtual machines, because limiting the CPU quota and physical memory allocation is relevant for them as well. The way Docker works in brief is there is a recipe of building an image, a file system, which is virtualized from the host file system and provides exclusive access for the container to use when it's running. I'm sure most people are familiar with that, so we can probably move on. What's important, what containers brought, is to not only build these images, but deploy them on any compatible hardware, which is today any x86 or even ARM or other architectures hosts. So a container built for one architecture can be deployed on any instance with compatible operating system. It's not perfect. They still share the host operating system, but it already creates quite better environment for reproducible runs and for isolation. On the other side, in the second way, what the industry did is made the virtual machines much more lightweight. One example, maybe most pronounced example today is AWS Firecracker hypervisor, which runs proper Linux and takes no compromises in security. So the way it works is that it uses KVM, which avoids duplication of the software of the operating system mechanisms, such as scheduling or guest memory management with nested page tables. It also leverages extensions for virtualization, such as page tables and virt.io and so on. At the same time, the most what they did is actually they really decreased the size of the code base by shrinking the emulation layer, boiling it down to just 2 types of devices, so one for NIC and one for disk, and the whole stack Firecracker fits into a couple of thousand lines of code of Rust. And it's also written in a type-safe language, which is Rust, to make sure that the probability of bugs is minimal. So Firecracker tries to combine both. It supports Docker-based deployment already, and it also can boot in much smaller time than even containers in many cases. So let's talk a little bit about the characteristics of the workloads. But before I can take questions about the isolation technologies, just maybe one question.
Hey, I have a question. Can you hear me?
Yep.
Is Firecracker able to, can it access all the device drivers present in the operating system? Let's say I'm running like 3-4 virtual machines, which I guess are on top of this Firecracker. And let's say I have like a few device drivers. Let's say I have some GPUs, right? Like 4 GPUs with NVIDIA CUDA drivers. So can Firecracker directly access it, or do I need to probably make some changes to the Firecracker kind of like in?
So Firecracker works in the same way as QEMU. When it relies on the bulk of the functionality on KVM already, but the rest of it you can implement in Firecracker code as well. And each VM would have its own stack, so it doesn't run many VMs in this sense. It's just the same way as QEMU works, where like each VM would have its own Firecracker code running in the root ring 0.
Oh, I see.
Thank you. Okay, so let's touch upon what are the workloads look like and why they are so different from conventional clouds. So the way people write functions is that they are short, because they break the code of their applications into pieces, and they want to achieve elastic scaling for every piece of their logic so that they pay a minimum amount of money and maximize parallelism where it's actually necessary. So this study from Azure called Serverless in the Wild, it has it shows that the average duration of a function is lower than 1 second. But some other studies in AWS Lambda say that can be even lower than that. So the recent study from 2020 actually says that in AWS Lambda, the median runtime of a function is merely 60 milliseconds. At the same time, functions are very cold. So in this chart, you can see the frequency of execution on the x-axis and the cumulative distribution on the y-axis. So you can see that 80% of functions are executed more rarely than once per minute. And obviously the CPUs and the operating systems were not built for this kind of workloads. And now you can also understand why providers try to pack up to thousands of these workloads per host, just because of these characteristics. There are more pointers on the workloads, which I'm not going you can read more about it on your own. We don't have time to discuss it in detail. So for the first pointer has more information about the requirements of serverless workloads, of analytics and other workloads when they are ported to serverless. With serverless in the wild has way more information if you want to know more about distributions, like interarrival time and execution time distribution and so on. And FAST, which is a paper from Francisco, who's gonna talk later, talks about the blob storage usage by these functions. So let's talk about the state of serverless today. What serverless brought to us is programming simplicity and pay-as-you-go billing.
Sorry, there's one more question on code functions. It's in the Zoom chat. Should I read it or can you see it?
Okay, I can see it. What is the general nature of these called functions in terms of performance requirements and so on? Well, the performance, if the functions are super short, then the impact of launching new instances for these functions on demand is huge. So that is why people try to avoid cold starts or optimize them somehow. So I guess this would be a brief answer to that. A more elaborate consideration of it is what additional resources are necessary, such as what it takes to launch a new instance. Like it imposes load on the disk, it imposes load on the memory, and so on. So this has to be considered from the provider side as well. I'm not sure if I can answer this general question in brief, but we can talk later about it. Okay, so programming is much simpler with serverless, and the costs are way lower because now you pay for invocations as opposed to for running services. At the same time, performance is not can be not as good as with provisioned resources, just because this is an elastic system which scales all the resources on demand. So the reaction of these systems may be slower to traffic changes because there is not enough over provisioning for the peak load. At the same time, some providers might try to over-provision resources, leaving instances of functions idle in case of load and spikes to a certain extent. But this would mean that the users, that the providers have to pay for it because they cannot really bill this to users. So this is a huge economical issue. Performance economical trade-off that a lot of works have been focusing on. Another important aspect is communication. Serverless functions are stateless and they cannot hold or share state among one another. And even instances of the same function cannot share state. And this is due to the requirement that any function instance should be able to process any invocation of that function it belongs to. The programming model with function invocations today is very simplistic and it doesn't provide a lot of room for optimizations. And this is where there's another call for innovation. And obviously there is security problems Because, for example, when you start sharing physical hardware among thousands of corunners, which is common in serverless, then all the side channel issues, all the interference issues, they all kick in again. So these are all entire directions. You can find many papers on some of them. You can publish your own papers on some of them. And I ordered them in, I would say, from the most published domains to the least published domains. And another thing, which was the case before this tutorial, I would say, leading cloud infrastructures are proprietary. And the main focus of our work that we did with the team is to develop an ecosystem for serverless researchers. Yeah, so here I would like to conclude this section and just say a couple of words about the tutorial. So you're gonna deep dive into, you're gonna dive deeply into the hands-on from the next sessions, and you'll learn about the benchmark suite called vHive and vSwarm, and how to use the ecosystem for performance analysis. And you'll learn how to do research in the infrastructure in different layers, as well as distributed architecture of serverless. Like, for example, how to trace serverless applications. And then we'll also show you how to study architectural aspects and implications, which is also part of the ASPOS abbreviation, right? Acronym. So thank you.